What you're looking at is a fully detailed 3D model of the J2 rocket engine, built from original NASA documents. How I got here and how the rocket engine works in detail you will discover in this video. The theory behind how rocket engines work and the different cycles an engine can operate on are quite accessible on the internet. One can find many articles, websites and YouTube videos that explain these concepts. And also in some sense they are quite good understandable, which goes against the common phrase, as long as it is not rocket science, it is not that difficult. Therefore rocket engine cycles are not the difficult part. Building functioning rocket engines is difficult. Because I would say that I understand basic principles of rocket engines, I wanted to look at real rocket engines and really try to understand all the components and get a really in-depth look on the construction of rocket engines. The first real rocket engines were developed during World War II, and the engineering behind them advanced a lot until the moon landing. Most major technological breakthroughs happened during this period. After this period, the advancements stagnated. Therefore, the new engines developed by 21st century manufacturers are still really similar to old engines and differ not that much. Because of this, old engine plans are still really valuable and could even serve as templates for new engines. I wondered which kind of plans I could find on the internet. Since most of the engines exist since 50 years, I thought that there must have been some document leaks. First, I looked at a really good video from the everyday astronaut, called The Entire Soviet Rocket Engine Family Tree. I was interested in engines like the RD-108, RD-120 and RD-168. In the video he showcases cut animations of all these rocket engines. But relatively fast I found out that all the cut models are only approximated renders from pictures, so they are not based on the real rocket engine plans. Therefore I started to do my own research and found a few good websites which are I think quite under the radar, like IPRE.com, where really detailed information about old rocket engines and a few technical drawings could be found, but still no complete drawings. I also found a blog named the Unwanted blog on upship.com, a guy who posts random things, mostly related to scale modeling. Connected to this is a community which searches for old physical aerospace engineering documents on eBay and other platforms, but I still not found detailed rocket engine plans. I looked through several forums as well, such as the Rocketry forum. There I discovered that Peter Arway is relatively well known within the community. He published some books for model rockets with original rocket structure layout documents, but not about the engines. Then I stumbled over the Secret Projects forum, where I found in some hidden post a link to a website where a document about the J2 engine was published. And there finally I found something that matched what I was looking for. The document was put together by a test engineer who was involved in the testing of the J2 in Sacramento, California. The 118-page long document is called J2 Engine Fact Sheet and includes mainly technical drawings. It is basically a complete technical drawing / manufacturing manual of the J2 engine. It contains basic system level schematics and overviews of the engine components. Also flow schematics with pressures, temperatures and mass flow rates, which could be used in principle to model the engine within MATLAB, SimScape or another program. It features really detailed drawings of the oxidizer turbopump, with detailed section views and component names. The same is true for the fuel turbopump. One can also find some assembly plans. In addition, detailed drawings of the injector, thrust chamber and nozzle are included. There are also in-depth drawings of all the valves along with descriptions of how they operate, as well as diagrams of the piping system. The drawings are from my point of view all in the correct scale, so angles, dimensions and proportions seem accurate and nothing looks distorted. However, there are no component measurements given, but if you find the size of one component, everything else can be scaled accordingly. When you look through these components, their functions and how complex they are, you slowly begin to understand that rocket engine cycles and the theory is really just the tip of the iceberg. The real constructions of the engines is rocket science. It is truly impressive that all the systems work so well together that they can go to space. The J2 Rocketdyne engine was used on the second and third stage of the Saturn V. The second stage was equipped with 5 J2 engines, where the third stage only used 1. The engine uses cryogenic liquid hydrogen and liquid oxygen and operates on a gas generator cycle. The system has a vacuum-specific impulse of 421 seconds and can produce a thrust of 1035 43 kilonewtons. The engine is 3.4 meters in length, has a diameter of 2.1 meters and a dry mass of 1,788 kilograms. And the chamber pressure is 52.6 bars. The J2 engine was first flown in 1966, but a modernized version of the J2 engine, the J2X, was considered to be used on a new SLS rocket from NASA. Development of the J2X started in 2007. The J2 was the base template for this engine, with really few design changes. This underlines the point from earlier, that rocket engine technology has not really advanced in the last 50 years. Included in the design changes were of course a new redesign of the electronics package and of the sensors. Also a new channel walled combustion chamber instead of a tube-welded chamber was designed. And lastly, instead of the axial hydrogen turbopump, a new centrifugal pump was designed. Now let's take a look at how the J2 engine actually works. As said before, the engine runs on an open gas generator cycle. In this engine model, liquid oxygen flows through the blue components, while liquid hydrogen, the fuel, flows through the red components. The green components carry the hot gases from the gas generator to drive the turbines. Parts in gray represent flight instrumentation and electrical packages. The light gray sphere is the startup tank and the black components are structural elements. The metallic looking components, for completeness, are the combustion chamber, injector and nozzle. To understand the operation process in more detail, we will start at the oxidizer side. Liquid oxygen flows from the propellant tanks through the oxidizer inlet and enters the oxidizer turbopump, where it is pressurized to high levels. Here you can see a section view drawing of the oxidizer pump. As you can see, the oxidizer turbopump is a really complex component. The oxidizer enters over the high pressure oxidizer duct, the main combustion chamber, and passes through the main oxygen valve. A tiny portion of the liquid oxygen is tapped off from the mainstream and enters through the bleed valve, highlighted here in light blue, the green gas generator. Let's switch over to the fuel turbopump. Here, similarly, liquid hydrogen enters through the inlet duct, the axial turbopump, and gets pressurized. Here you can see the section view drawing of the axial turbopump. It's also a really complex component. Once pressurized, the hydrogen exits the axial turbopump and enters the high pressure hydrogen duct. From there, it reaches the main hydrogen valve. After passing through the valve, the hydrogen flows into the fuel manifold, which distributes the fuel into cooling channels around the nozzle. Finally, it enters the main combustion chamber through internal channels. Again, before the flow enters the high pressure hydrogen duct, a small portion of the fuel is tapped off from the fuel bleed valve and fed into the gas generator. Here you can see a cutaway drawing of the gas generator. Inside the gas generator, the oxidizer and fuel is injected into the combustor and ignited. The hot gases from the gas generator enter directly the fuel turbopump turbine. The turbine in turn spins up the axial pump, and that way the pressure is generated. A tiny part of the generated gas that leaves the turbine enters directly a manifold. There the gas accesses separately the nozzle to create thrust. The main part of the gas flow enters the gas duct, which moves the gases to the oxidizer turbopump turbine and spins it up. Again, the turbine drives the oxidizer centrifugal pump, which creates the pressure for the gas generator. After the oxidizer turbine is spinned up, the gas has done all its work and enters the main gas manifold duct and is also introduced into the main combustion chamber. At this point, all major fluid paths are in operation and the cycle continues until the propellant tanks are empty. The re-engineering of the J2 engine continues in the next parts of the series. Subscribe if you are interested.